Okay, we've got this circuit which is intended to investigate the variation of resistance of this thermistor with temperature. Okay, give 3 modifications to the circuit so it works correctly. Yes, there are 3 things wrong with this circuit at the moment. Well, first thing are the 2 cells. They're facing in opposite directions, so they're both trying to send current in the opposite direction. So the first thing it needs to change are the cells. Just get them pointing in the same way. Doesn't matter whether you point them that way or that way, as long as they're in the same direction. Good. Second thing, look at that. You never connect a voltmeter in series. Never. Okay? The voltmeter should be connected in parallel. That means parallel. So the voltmeter should be connected the way the ammeter has been connected. All right, so that should be there. And that brings us on to the third mistake. You never connect an ammeter in parallel like that. Ammeters are always connected in series. So the ammeter should be connected in series. So the ammeter should be where the voltmeter is. Good. Okay. Right. So we have this set up to measure the temperature of the thermistor. Okay. A water bath, a thermometer. Here's the thermistor and a stirrer and a heater. Give 1 reason for using the water bath. Okay. So it's asking, why do we have to go to all this trouble to measure the temperature of the thermistor? Why don't we just have the thermistor in the air, surrounded by air on the bench, wherever this circuit is, and the thermometer next to it? The reason is, by surrounding the thermistor and the thermometer in water and heating it but stirring it at the same time, you ensure that whatever the temperature of the thermometer, it'll be the same as the temperature of the thermistor. So by having this set up, you're ensuring that you are getting an accurate reading of the thermistor temperature. Okay? That's it. So you ensure that the thermometer reading is the same as the thermistor. Temperature. Okay? That's the whole idea. Good. Okay. So this equipment apparently is suitable for temperatures from 20 degrees C to 100 degrees C. State 1 way the student could develop this experiment to investigate temperatures outside this range. Okay? Well, at higher temperatures, what's going to happen beyond 100 degrees C? The water boils and turns into a gas and disappears, so it's useless for going beyond 100 degrees C. So we need a substance, a liquid substance, whose boiling point is higher than 100 degrees C, and that would be oil. Okay, so in the exam write oil or any liquid that has a boiling point greater than 100 degrees C. That way you can investigate temperatures greater than 100. Okay, now the question said it only wants 1 way, so don't write 2 ways in the exam, but I'll give you a second way and you can choose which one you prefer. You could also use ice. Stick with water as the liquid, but chuck in some ice and that will reduce the temperature below 20 degrees C. Without the ice, you won't be able to get it below 20, which is sort of room temperature. But ice will take the temperature to less than 20 degrees C. So pick one of those for the exam, whichever you prefer. Good. Right. This thing now. The student takes measurements for two other components, A and B. Okay, so we're not looking at the thermistor anymore. We've got these mystery other components, A or B, in that position there. And you get these results. Okay, I've tried to recreate reasonably accurately what's on the exam sheet. Right, compare and contrast how the resistances of component A and component B vary with temperature. 3 marks. Okay. Exam technique, here we go. We've got to extract 3 marks from this. So, it says compare and contrast. So what you're looking for are ways in which these two are the same and ways in which they're different. Okay? So, if we can come up with at least 2 ways in which they're the same and 2 ways in which they're different, we've definitely got 3 marks. So, we can say that they are, for both of them, so how should I do this? Similarities. Okay. For both of them, okay, I know I bang on about this in all questions like this, but it's really important. Exam technique. Say the obvious. You get marks for saying what you might not think you get marks for. Just say the obvious. For both of them, the resistance changes with temperature. Okay? So, resistance changes with temperature. Okay? Pretty obvious, right? Look, the resistance changes as you change temperature. Okay? Say the obvious. What else? Okay. Well, in both cases, this line is not straight. It's curvy. Okay? So, to say that in a clever way, you say that they both have, there's a non-linear relationship between temperature and resistance. Non-linear relationship between temperature and resistance. Okay? Right, differences. First difference. Well, the obvious one, the obvious place to start is to say that for A, temperature decreases, resistance decreases with increasing temperature, whereas for B, resistance increases with increasing temperature. Okay, so I'm going to write this like shorthand, but you obviously have to write it out in full sentences for the exam. So for A, resistance decreases with temperature, and for B, resistance increases with temperature. Okay, we've already got our 3 marks, but I've got some other differences as well, if you want to add them. Nothing wrong with saying 4 things in a 3-mark question. Right, I think those are the important ones though, they're the main ones. So, you can also say that for A, the greatest rate of change is at temperatures below about 20 degrees C. Okay, here this is the steepest part of the graph. Okay, so for A, greatest rate of change of resistance, so temperatures below 20 degrees C, whereas for B, this is clearly the steepest bit. So for B, the greatest rate of change of resistance is for temperatures greater than 90 degrees C. Okay, this is a bit overkill now, okay, it's only a 3-mark question, but it's good for you to see all the possible things you can say. Right, finally, last thing we're going to say, for B, the resistance is constant for temperatures from 0 to 50 degrees C. See, it's flat there, yeah? Whereas for A, it's never flat. It gets close to being flat here, but it's not flat. So just say the resistance is never constant in the temperature range from 0 to 100 degrees C. It's important just to say from 0 to 100 degrees C, don't claim it's never constant because you don't know whether it would become constant temperatures greater than 100. Okay, good. Right, that's more than enough for that question. Final bit. I'll just change colour to differentiate it. So, right, component A is connected to a 12-volt supply. Right, so we don't know what component A is, whatever it is. It's connected to a 12-volt supply, so a different circuit. It's just component, whatever it is, component A. Component A is connected to a 12-volt supply like that, okay? What is the current in A at 80 degrees C? Right, so here's the graph for resistance and temperature. They've told us it's at 80 degrees C, so we clearly have to use this to work out what the resistance is at 80 degrees C. So you go up and along, find 80 degrees C, go up and along, and it turns out to be 5,000 ohms. I've written this in kilo ohms, so it's 5,000 ohms, right? So our resistance is 5,000 ohms. Okay, we've been told that voltage is 12 volts and we have to work out the current. So we're going to use the formula V equals IR. You really need to know this equation, okay? If you don't know it, commit it to memory for eternity right now. It's a very important equation that you'll need for your exams. It tells you how voltage, current, and resistance are all related. V equals IR. And we want the current, so we have to rearrange to make I the subject. Divide both sides by R, and you get I is V over R. We've got V and R, so therefore I is, voltage is 12, resistance is 5,000. That's it. I is 12 over 5,000, which was answer B, if you're interested. So that's it. Good. So I need you to go away and remember that equation. Okay? V is IR. Very important.